Thank you very much for the kind introduction and also for just the invitation to come over here. Turns out to be a very nice time of the year to be in Washington. It's still warm and not too warm. So I enjoyed it actually quite a lot. Yeah, so what I would like to tell you about in the lecture is about our work on topology in open systems. And so I probably don't have to tell you too much about on the point of motivation. This is like carrying owls to Athens. So we are interested in topological states basically for two things. The one thing is that they are known to have very interesting exotic quantum states are connected to topological systems. For example, excitations in fractional quantum Hall systems can have abelian or even non-abelian anionic statistics. So a lot of interesting things can come up here. And secondly, because there are integer quantum numbers, whenever you bring together two spatial regions with different integer quantum numbers, then something has to happen at the interface. And what is happening there is that there are edge states or edge currents which can be protected. And so there's a lot of interest in the topological protection. But the questions actually which seem to be a bit open, and this is the ones which I would like to address, is the first thing is what actually happens if we go to a system at finite temperature? So what is actually surviving of topological features at finite T? And secondly, and maybe even more importantly, is the question, can we make sense of topology in non-equilibrium systems which are driven and open systems? Now, why is that interesting? Well, if we have an open system, for example, described by a Lindblad master equation, which have some eigenvalues, and if we are considering a system which is gapped in the sense that the spectrum of these lambdas here, or more precisely the real part of these lambdas, they define the rates at which the system approaches a steady state. So if there is a finite gap, a finite damping gap, then what it basically means is that, and there is a unique steady state, so there's only one state with an eigenvalue lambda equal to 0, then what it basically means is that the state is an attractor of the dynamics. And if you start to kick the system out of the steady state, it will by itself return to that state. And if the rate of kicking it out is smaller compared to this damping gap, then essentially this state is protected by this mechanism. You are protected against these perturbations. So the questions connected to that is, can we actually combine topological protection with the built-in protection of open systems which return the system always to the unique steady state? Now, much is actually known about topology and non-interacting fermionic systems. As you all know, one can just classify Hamiltonians of three fermions, basically in terms of three symmetry properties: time reversal, charge conjugation, and a combination of the two. And out of this, you can build this famous tenfold periodic table of all possible topological classes. And for that reason, and actually little less is known, or less is known about topology in interacting systems, and which is a completely open question, what is the sense of topology in mixed states and in open systems? And, but in some sense, I would like to restrict myself in most parts of this talk to something which is very close to free fermions, namely these are non-interacting Gaussian open systems. So a Gaussian system is one where the density matrix can be represented in a form like this, like with the help of a single matrix. This is a single particle correlation matrix. So all information is encoded essentially in single particle correlations. And these Gaussian systems are systems where the Hamiltonian is quadratic in the creation annihilation operators, and you can have couplings to reservoirs described by Lindblad generators, which are linear in fermion creation and annihilation operators. So this is a very general class of systems, and all of them are Gaussian, and this is what I want to talk about today. Okay, so I will start and remind you a little bit about topological invariants, at least some of them, and then point out that there's a very important relation to a quantity which is called polarization. And then I will talk about how this polarization can actually be used to classify topology also for mixed states. And I want to exemplify this with two examples. Namely, I will have a look at a so-called topological pump at a finite temperature. And then I will look in an equivalent topological pump where the pumping is actually induced by couplings to reservoirs. And out of this, I will then argue that I can construct a generalization of a topological phase, an ensemble geometric phase, which allows us to classify a topological systems of density matrices. And this ensemble geometric phase will be shown to be directly linked to the polarization. One thing which comes up in this construction is, as you will see, an effective Hamiltonian. And we'll talk a little bit about how one can actually realize the effective Hamiltonian. And then if there is still some time, but I doubt that, I will actually also talk a little bit about interacting systems, namely that these ideas here can also be used to transfer topological properties from interacting systems to non-interacting systems, and in this way also detect them. Okay, so let me start with something which you may know all very well, namely about topological invariants. In many cases, it is topological properties are quantified in terms of geometric phases, like the Zag phase, basically just telling what happens, what phase is picked up if you change the Bloch state in the Broglie zone, and then if you have a Hamiltonian which depends on a parameter lambda, and you make in a periodic way, and you're looking for the winding of the Zag phase, if you go in the parameter space on a full loop, then this defines a topological invariant, which is a winding number. And in 2D, you don't even need an external parameter. You have an internal one. For example, if you have a two-dimensional lattice model, you have the momentum in x and y direction, and then you can replace this lambda here by the momentum in one of the two directions, and then what you end up with is in 2D the Chern number. But most importantly, both of them rely on the fact that you can define something like a geometric phase. Now, an important observation by Towles and co-workers in the early 80s was that this change of the Zag phase is directly related to transport in a bulk system. So if you're in a periodic way change in Hamiltonian in a one-dimensional system, for example, then you find that there is a transport which comes in quantized units. And just to give an example, let me start with a very simple one-dimensional topological model. This is a Zhu-Schrieffer-Hager model. What this is essentially a 1D superlattice with an alternating hopping, and there are fermions. And this model has chiral symmetry, so it anticommutes with an operator sigma z. And we consider the case where it's at half filling. So because the unit cell consists of two lattice sites, this is a two-band model, and we consider half filling, so the lowest band is filled. Now, turns out that you can, when you calculate the Zag phase, then you have to define a reference point, and depending on where you take this reference point, namely either cutting a weak bond or cutting a strong bond, you get two different values. If you look at the bulk of these two phases, they look the same. And also the spectrum looks exactly the same. The only difference is that we have exchanged the tunneling rates T1 and T2. So there's no difference in the bulk, no difference in the spectrum. But if you calculate the Zag phase, you realize in one case it's 0, in the other case it's pi. So they differ. Now, there's no direct way of connecting one phase into the other just by moving the T1 and T2, because you have to go through the point where the two bands touches. which happens at when the two tunneling rates become equal. There is, however, a way of avoiding that, and this is if you break the chiral symmetry by adding a staggered potential, which shifts the even sides down, say, and the odd sides up. And this is a model which has been considered by Rice and Mehle also in the early 80s. And this is one of the paradigmatic models of a charged pump. Namely, what you can do now is, now you have a two-dimensional parameter space. You have this staggered potential, and you have the difference between the two hopping amplitudes. Along this green line here, this is the line of the Zhu-Schrieffer-Hager model, which had different Zag phases on the left and on the right. They differ by pi. And we couldn't go through this along these lines here because then there's a bend closing point here in the center. But we could, in principle, go around the parameter space. And now what's going to happen if you do this, let me start on this side, and let's consider a case where there's no particle in the left lattice side here. Then if we go around this loop, then what's going to happen is that you end up with exactly the same bulk state, but now there's one particle sitting at the edge. So what has been done here is a transport of exactly one particle through the whole lattice from the right to the left in this case. And this is a charge pump which goes back to towers. Now, so as I show you, and as you probably know very well, there's this very famous relation between the changes of the geometric phase or the Zag phase and topological pumps. But now what's going to happen if you go to systems with a finite temperature? If you have a finite temperature, then the system is described by a density matrix, and as a consequence, we don't know a priori what the Zag phase is, what meaning the Zag phase has. So the Zag phase is out of game if you want to define topological properties. Now, how about this charge pumping? Well, this is actually a calculation when a group from Matthias Treuer. It shows the transported charge as a function of temperature. And as you can see, as soon as the temperature becomes comparable to the gap between the two bands, then this quantized transport breaks down. The reason for that is very simple, because if you are on the lower band, then the transport goes in the one direction. If you're on the upper band, the transport goes in the other direction. So as soon as you have some finite temperature, you mix up the excited band, and then these two effects cancel, and the transport is, strictly speaking, no longer quantized. So as soon as we go to finite temperatures, mixed states, unfortunately, rule out both. They rule out the Zag phase and the quantized transport. Turns out, however, that there is a third quantity which is strictly related to the two, and this is the many-body polarization. And I want to argue now that while these two quantities cannot be used anymore as soon as we go to mixed states, the polarization can. Now, what is the polarization? Well, basically, this goes back to a work by King, Smith, and Vanderbilt, and also in the early 80s, who showed, again, that for ground state systems, the change of the Zag phase is directly proportional to the change of the polarization, modulo the lattice constant. And what the polarization is in essence just the center of mass of an electronic wave function within a unit cell. So it's the weighted expectation value of this one-year wave function. But I'm not going to use this expression because in a translation invariant system this is ill-defined. But I use an expression which goes back to Resta, which is applicable to periodic systems. So what Resta showed is that these two things are identical. His definition is you take the expectation value of a momentum shift operator, where x is the center of mass of the wave packet in the ring, and you take the logarithm and then the imaginary part of it. What you see immediately is what this defines is a phase. So as a consequence, if you change parameters in a periodic way, you start from a certain state and you go back in a periodic loop to the same state, the phase has to come back to itself or to multiple of 2 pi's of it. So from that point of view, it is immediately clear that the polarization will be a quantized quantity provided that you make periodic changes in a state. And the second thing to observe is that the polarization is, of course, well-defined also for any state. Could be a mixed state here, and in fact can be also be ground state of an interacting system. So this is well-defined. And the last remark is it is intrinsically a many-body quantity, because if you expand the exponent, you get also all order correlation functions. Okay, so now let me have a look and see what happens if we now look exactly to the same type of topological pumps, for example, the finite temperature Rice-Mehle model. And now I'm looking at the polarization. Now what is shown here is the polarization as a function of the parameters T1 minus T2 and delta at t equal to 0. And as you can see, if I start anywhere and I make a loop around the singularity in the center, the polarization winds by 1 unit. And that is exactly corresponding to the particle transport as we have seen before. Now, if I switch on a finite temperature, particle transport breaks down. But if you look at the polarization, the shape does change. But what does not change is the winding. So the winding of the polarization still remains, even though we look at the temperature, which is much, much higher than the energy gap. So in essence, although we have almost a 50-50 population in the two bands, what the polarization picks up is still the majority of the occupied bands. And in fact, it turns out that this winding remains all the way until I go to infinite temperature and then switch to negative temperature, which is possible in the two-band model. So what you see here is a polarization winding as a function of this angle. For a positive temperature, it goes in one direction. And then only if I go to infinity and go to negative temperature, you see that everything is reversed, simply because then the two bands exchange their role. Okay, so there is a topological phase transition, but only at infinite temperature. Now let me also show you that these concepts can even be applied to systems where there is no Hamiltonian. You had a question?
So in this one, again, you have two bands, but then you're saying that even at finite temperature, you don't have a positive polarization and negative polarization that cancel each other?
Yes. That's exactly the statement.
And why is it so different than the...
That's, of course, exactly the question I should answer, and wait a little bit. I'll come to it. Okay, so what I would like to argue is that this whole concept can also be applied to systems where there is no Hamiltonian counterpart. And this is a model which we looked at 2 years ago. So here we have a lattice of fermions and in a one-dimensional lattice of fermions. And we have lattices J plus 1, J minus 1, and there's a unit cell of 2. And now we look at the system coupled to reservoirs only. We could add a Hamiltonian, but it's not really relevant here. And there are two types of reservoirs. One reservoir always coupling within a unit cell, and a second reservoir which couples the adjacent neighboring unit cells. And as you can see, the Lindblad operators here are linear in the fermion creation and annihilation operators. So this is a Gaussian system. It has a unique Gaussian steady state. And now they actually, let's have a look what these Lindblad generators are actually doing. If we, for the time being, set this, there are two parameters, epsilon and lambda. So if we set this parameter epsilon equal to 1, then this term drops out. And what these terms are doing is essentially that it takes out fermions on the right side of J, of lattice side J, and puts it into the left side of J, so that this reservoir is actually pumping from here to here. And this reservoir takes again out particles on the right side of lattice side J and puts them into the left part of J plus 1. So this one pumps into here. So in other words, if lambda is equal to plus 1, we get fermion pumping from the green side into the blue sides. And if we do it the other way around, then we get the pumping from the blue sides into the green sides. And then there's a second parameter which basically controls how much coupling is within the unit cells and how much coupling is between the unit cells. These are now our two parameters. And if you look at the polarization and calculate it for the steady state of this system, it says here TBD simulation. In fact, that's wrong because it's a Gaussian system. We can do it analytically, almost analytically. This is from a related spin model. This is no longer Gaussian, but OK. Never mind, the figure is correct. So yeah, as you can see, if we go around now here in this parameter space, again around the 0 point, then there's a winding of the polarization, and that defines a topological invariant, even though we don't even have an Hamiltonian. There's now no underlying Hamiltonian which characterizes the system. There are two more interesting observations. Also, this model has a chiral symmetry, namely along this axis here, and along this axis, the polarization itself is quantized, not just the winding around the center point, and it differs exactly by 1/2, similar to the Rice-Mehle model. And now I started my talk with a motivation. My talk with a motivation that we would like to combine topological protection with a protection which results from coupling to reservoirs. So the one thing that I would like to see is that topological features survive losses. And typically, if you have an edge current, in a quantum Hall system, and you have some disorder, then it just goes around the disorder, so it's robust. But if you have a loss channel at the edge, then of course the current is gone. And our hope now is that in these driven open systems, they can be made robust also to losses. Okay, so here is this system and the winding of the polarization when you add Hamiltonian disorder, and well, you see there's not really much going on as you would expect. But now the interesting thing is if I add losses to the system, also nothing has happened. So the polarization winding remains the same, and at the symmetry protected points here at 0, pi, and 2 pi, also the polarization itself stays exactly quantized. Okay, so there is some robustness to disorder and even losses. Okay, so but now comes the question: how do we understand that there is this topological invariant, the integer invariant, even for mixed states? So for this, let me first start with some observations from some numerics. So this is here again the polarization in the finite temperature Rice-Mehle model as a function of this angle for different temperatures. For t equal to 0, we have the center line here, and if you increase the temperature, then the curve goes more to these step-like functions. This is a simulations for lattice of length of 8 sides. If you go to 64 sides, then the picture looks like this. And if you keep increasing the number of sides, then you notice that these curves at finite temperature approach more and more the result of the ground state. And in fact, what you can show analytically, or what we could show analytically, is that there is a mechanism which brings the polarization of the mixed steady state, makes it equal to the polarization of a pure state, plus a correction which scales away with system size. And this state here, this pure state, happens to be the ground state of an effective Hamiltonian. And this effective Hamiltonian is just a single particle fermion Hamiltonian with a single particle correlation function of the mixed fermionic system. So in other words, what we can show here is that all the polarization properties of this mixed state, be it a finite temperature state or be it a state which doesn't even have an Hamiltonian, so of a non-equilibrium system, that can be related to an effective Hamiltonian. Now, if you look at the winding of the polarization, then the winding of this polarization actually has to be exactly the same than the winding of the ground state of this pure state. And the reason is the winding of a polarization has to be an integer. This also has to be an integer, and this also has to be, therefore, an integer. But the only integer which is compatible with the fact that it scales away with system size is that if this integer is 0. So as a consequence, the winding of the polarization at any temperature of any mixed state is always the winding of the polarization of this pure state. And now, of course, we can apply all the machinery which we know very well, because now we have a ground state of an Hamiltonian, and we can associate to it a Sachs phase, and that actually defines what we call an ensemble geometric phase. Now, it also, so everything is encoded essentially in this effective Hamiltonian. In fact, in a work by Charles Bardeen and Sebastian Diehl some time ago, they already thought about classifying the symmetries, classifying the topology of open systems by using exactly this effective Hamiltonian. And now we have seen why this is exactly the right approach. It also allows us. Yep.
So is this a general result, or you sort of first started with this example, Rice, Manley, and then you said sort of?
No, this is a general result for all Gaussian systems.
All dimensions.
And also in all dimensions, and this is actually in the paper which is mentioned here somewhere, is focused mostly on one dimension, but one can extend it to higher dimension. Now, it also allows us to understand a couple of things. Namely, we can ask ourselves, when is there a topological phase transition? Well, it can happen if the gap of this effective Hamiltonian closes. So this is this closing of the so-called purity gap. This is the gap of this here. Or it can happen if the damping gap of the original Liouvillean closes, meaning that we don't have a unique steady state anymore. So that could, of course, also happen. And there are some extensions to interacting system, but I will not talk about this today now. So now, this, by the way, explains why we have seen that the phase transition at infinite temperature, and only at infinite temperature, because for thermal states, one can easily show that this single particle correlation matrix is basically proportional to the Hamiltonian times the inverse temperature. So a phase transition can happen only under two conditions, namely either if the gap of age closes, so if you are at a critical point, or if the temperature becomes infinite, so beta goes to zero. Yeah.
So I have a question about this result at infinite temperature. So if I'm understand correctly, infinite temperature basically means that you populate uniformly everything. So you have one band with whatever index plus 1, the other band with whatever index minus 1. So how come they don't cancel out?
Oh, they do. They exactly cancel out at infinite temperature. There's no winding of the polarization.
So you just uniformly populate two bands with opposite topological indices. So where are they going to cancel?
Yes, they do.
So,
but that's exactly what is shown here, right? I mean, the winding of the polarization for positive temperatures is -1. For negative temperatures, +1. And at zero temperature, at infinite temperature, there's a phase transition. So the polarization is not defined anymore. So far, these are non-interacting systems. Yes, yes. Well, maybe I can just show. No, it's okay. Okay, so, and it also, by the way, explains in the driven model the singularity here at epsilon 0 and lambda equal to 0, because if you, for this model you look at the damping spectrum, so the spectrum of the decay rates, then nothing special happens. But if you look at the spectrum of the single particle correlation functions, you see that it actually touches here at this point. So there is a singularity, and if you go around it, you pick up a geometric phase. Okay, so now, of course, you could ask the question, can we somehow realize the effective Hamiltonian? We have seen that we can use it to classify the topology in the system, but how can we actually, is there actually a way of seeing this effective Hamiltonian? And the idea here is the following. We couple our system, which is at finite temperature, or is a driven dissipative system, to a second auxiliary system of fermions at t equal to 0. And the coupling, and then let me describe the fermion operators of the original systems by A, J, and AJ dagger, and the fermions of the auxiliary ones by C and C dagger. And the ideal coupling which we would like to realize is a density-density coupling in momentum space. Now you will ask, how can you practically realize it? If you're interested, I can tell you in the question sections. But let's assume for the moment that we can do it. And so here alpha and alpha prime are basically the band indices, because this system will have multiple bands, and we have to sum over these bands. Now, suppose this coupling is weak. If this coupling is weak, then the lowest order approximation to find the dynamics in this auxiliary system would be a mean field approximation, meaning that we take the operators of the driven system and just take their expectation value. So, but if we do that, if you replace the operators by the expectation value, then starting from this Hamiltonian, now this here becomes a number, and all what this is then a Hamiltonian, free fermion Hamiltonian for the auxiliary system. And the Hamiltonian matrix is exactly the single particle correlation matrix of the driven dissipative system. So as a consequence, if there is a winding of the polarization in this in this quantity here, then we will have a winding now of our fermionic system, a polarization in the fermionic system. And since the fermionic system is assumed to be at t equal to 0, now there is a strict relation between the polarization winding of the auxiliary system and particle transport. And now we can clearly see the particle transport at t equal to 0. Oh. Okay, sorry. So sometimes these problems at exactly this point. So that this actually works is shown here. So this is this driven dissipative topological pump, which I showed you. We had in the open system, we have this winding of the polarization, and we have a coupling to the second fermionic system, and this is a particle transport. It's actually calculated on a torus, so this point and this point are the same. So you see that there is a particle transport in the auxiliary system. So it works. Now, of course, you may ask a question. You are coupling a system at finite temperature to a t equal to 0 system. So what's going to happen is that this finite temperature system will heat up the other one. And you have to worry about this heating, because only if the auxiliary system here is at t equal to 0, there is strictly speaking a quantized transport. So what we have calculated now is the purity of this auxiliary system, and as a function of this angle in this model, and extracted the heating rate. And it turns out that if you increase the ratio of the damping gap of the dissipative system towards the coupling between the two, then the heating of the auxiliary system can actually be suppressed, and the heating rate goes down, and therefore there is a knob which you can tune to make sure that your measurement system is really at 0 temperature. Okay, so since there is indeed some time left, then let me also tell you a little bit now about interacting systems rather than Gaussian systems. And so the idea here is, can we actually use the same trick, namely the coupling of our system of interest to a free fermion system, to somehow transfer topological properties from one to the other. And the model which we looked at is an extended superlattice Bose-Hubbard model. So these are bosons hopping on a 1D lattice with alternating hopping rates T1 and T2. There's an on-site interaction U, and there is a nearest neighbor, and in fact also next nearest neighbor interaction. In this case, it's only nearest neighbor interaction V. And if you look at the phase diagram of of this model, you find, besides the known phases which exist in the superlattice Bose-Hubbard model. First of all, in the simple Bose-Hubbard model, there are the mod insulating phases at 0 filling, and then at 1 filling 1 somewhere up here. And then as soon as you add this superlattice, then you get other phases like the half filling, simply because you split the bands here by introducing the 2-lattice side unit cell. But then, due to the non-local interaction, you also get other insulating phases, like, for example, the phase with 1/4 filling. And so now let's have a look at this phase, which has 1/4 filling. And to understand why this is a ground state of the system, we can look at an atomic limit where the maximum of one of the two tunneling rates is very large, the other one is small, so the maximum is much larger than this non-local coupling, and the minimum is much smaller than that. Then this allows us to reduce this lattice of double wells basically to a single lattice where only the lowest state of each double well is taken into account. And then the interaction just makes sure that there is a ground state where you have a charge density wave at, say, every second sides. So you immediately see at quarter filling there are two degenerate ground states, both at quarter filling. And as a consequence, the classification of the phases in that system is a bit more involved. You need actually two things. You need you can use the many-body Zack phase, but also you need also one more classifier, namely the inversion at the odd bonds. So, for example, if you make the bonds here, say on this between these lattice sides, then there are these four phases. These two break the inversion symmetry. These two do not break the inversion symmetry, but they can be distinguished by looking at the Zack phase. So if you calculate the Zack phase here, it is 0, and if you calculate it here, where there's a particle, where you cut through a particle, then the Zack phase is actually pi. So so you have now four different phases, and as a consequence, you would expect, if you now do a charge pump in the parameter space of delta and T1 minus T2, then after one full cycle of this pump, you turn actually one of the two ground state into the other one, and not going back all the way to the original state. That is actually related to so what you would expect is a fractional charge transport, in this case just by charge 1/2. Yeah.
If your V is infinity, so it becomes essentially, or rather maybe U is infinity, it becomes essentially a hardcore boson or spin, which is equivalent to Haldane spin change, right?
Mm-hmm.
So, which has two phases and it's kind of exact one-to-one mapping. So do you reproduce this?
Actually, we haven't looked at it, I should say, but we should, yeah.
All interacting phases have been classified, right?
Oh, yeah, no, I'm not claiming. No, I'm not. I will not say anything about the new about classification. That's not the purpose. What I wanted to say is just to give an illustration that this idea of coupling an interacting system to a non-interacting one and transferring the topological properties from A to B can I mean, I have used this for finite temperature and open systems, and I'm saying I can use the same type of idea for interacting systems. That's all what I want to say. I'm not saying anything new concerning classification, just using a different way of classifying it.
So, I'm sorry, this is, how is it an open system actually? So you just showed basically Fermi multi-dimensional totally closed system, right?
That's a totally closed system.
So why is it open system?
No, this is not an open system. I talked about open systems before, and now what I just wanted to illustrate is that there may be a common ground where we can understand topology in mixed systems and also in interacting systems, but now for pure states. Yeah. Okay, so coming back to this charge pump here, here we will expect that there is a fractional charge transport by only, you have to basically go twice in order to move one particle. And now let's do exactly the same thing. So couple the system to our auxiliary fermion one. And this is done here with TBD simulations. In this false color code is the population of the lattice sites. This is a boson system, and so it's finite. So we cannot really nicely simulate periodic boundary conditions. So we're looking at a finite system. We start in a case where there's an occupied edge state here on the left and an empty one on the right. And then there are these half-filled double wells here in the middle. And if you go through the pump, you see that you move this edge state from here to here, but also in the center, the particles shift. So at the end, you have moved exactly one half a particle to the left, to the right. Now, if you look at the fermion system, you can see almost no difference. So it basically follows the bosonic system. Yeah.
Two different questions. So, with respect to this simulation, are you using a sort of mean field connection between these two simulations?
No. This is full quantum theory, of course, not mean field.
Question, so to what extent is this sort of Coulomb drag effect?
Oh, that is Coulomb drag.
I mean, it seems like
that's exactly what we. That's the whole story. Yes, that is exactly what we start off. So, I mean, the Hamiltonian at the beginning is exactly this, right? Well, where did I have it? This is exactly what it is. Well, it turns out it's not Coulomb here, but it's a density, attractive or repulsive. In fact, it turns out that you have to use repulsive interaction just for heating reasons, but well, that's some details. But yes, you're right. I mean, that is exactly what it is. But you had a second?
No, that was the second.
Oh, this was the second.
Just the HAD simulation.
Oh, yeah, sorry, yes. Yeah. Okay, so now if we look a little bit more in detail and make some cuts through different bonds, we can also look at the transported charge through these bonds. And then you see if we take this green bond here, then in this cycle, there's never ever a particle going through. If you take the magenta one, then very early on there's a transport and then nothing happens. If you're on the yellow side, then in fact the whole particle goes through because the particle goes from the left of the yellow line to the right. And if you make an average, you end up with exactly 0.5 as you would have expected. So there's this fractional transport. Okay, so let me summarize. So what I wanted to tell you today is that we can make a classification of open Gaussian systems or finite temperature Gaussian system by introducing an effective Hamiltonian where the Hamiltonian matrix is a single particle correlation function. And I have shown you that one can define an ensemble geometric phase by looking at the many-body polarization of these systems. And if the system is gapped, then you can make a loop in parameter space. And if you make a full loop in parameter space, the change of polarization is quantized. And then, in fact, is given by the Zach phase of the ground state of this fictitious or effective Hamiltonian. I showed you that one can actually realize this effective Hamiltonian by coupling the system to a second one, auxiliary one, and then also that we can can extend these ideas to couple interacting to non-interacting systems. And then finally, let me thank the people who are involved, from students, former student of mine, Dominik Linsner, and to a PhD student and master student, Lucas and Uri, and we had a fruitful interaction with Charles, Sebastian, and Alex, and these are the sources of money. And with this, I would like to thank you for your attention. And